Let's go to week 7 where we now deal with DC circuits. Okay, week 7 is now on DC circuits, and week 5 or 6 was just current of electricity or current electricity, whatever. Okay, it's just electricity which is flowing. Now we're doing week 7. Let's see how it goes. What are the formulas that we got to remember here? So, first of all, we have to remember the formula for EMF, and you know what it is? If I put a circuit like this, okay, and we get let's put just a bulb or something like this. You know, a bulb is like that, then like this, then you circle it. Okay, so here's our bulb. Now let's say that this is 25 volts and this other part is going to be 10 volts. If I say 25 minus 10, I'm going to get 15, and you can see it written here as 15 volts. Now this 15 volts is going to be the terminal voltage if we take between this terminal and this other one. It's going to be the terminal voltage. But then we would have ignored the space that is in between them. Voltage just means a potential drop. This is just how much energy does your electron move as it goes around a circuit. Okay, and we'll be looking at not just one electron, but many of them. We'll call it a coulomb of them. Okay, a coulomb of charge, which is a coulomb of electrons, which is a lot of them. So how much energy do they lose when they go around a circuit? So if we take when they go around a circuit and we don't also include the energy they lose as they pass back through the source, because in reality, the source actually has, there's actually some space. This is the longer bar, the shorter bar. There is some space in here, which the electron will have to move, and it can lose energy in there as well. So we must now, in this week 7, start to also include the energy the electron or the coulomb of electrons will lose as they pass through the source. We've seen the energy that they pass right around the circuit, but we can't say a complete circuit if it's not coming back right where it started. So it's going to have to go right round and come right where it started, not to end at this side, but to come all the way back to here. So how much energy would that electron have lost? Or then, because it will gain again in the source, but how much energy will the electron go through if we're looking at only the losses? Well, there's going to be a loss due to the lamp outside, which is a resistor, R, and then there's going to be the inside of the source has a small resistance also, which we'll call R. Now, if we are looking at the energy loss, we're looking at the potential drop, the V. So, and delta V, we know it is IR. So, to then find the delta V here of the source is going to be delta V is equal to I small r now for the resistance of the source. So now when we want to find the total EMF, EMF is the energy that you need to drive the charge right around the whole circuit and go back where you started, to mean you are passing through the source again. And that EMF will be, we count the potential difference outside, the delta V outside, then we also count the one inside, and this will give us our E. So remember this formula for E. Then we need the formula for maximum charge, which is going to be CE. This is going to be the formula for maximum charge of a capacitor. Okay? If you are talked about to find the maximum charge and you're dealing with the capacitor, you're going to put this one. Now, the other formula which we can move on from here to then go and do is going to be the power supplied. So you should know that if we now ask for power supplied, the total power supplied, it will be, instead of VI, it will be EI or IE. Okay, because it could have been IV, VI is also, but we are now using E instead of a V. This is going to be the power generated. This is going to be the power generated. Okay, the power generated. Then for us to then get the power delivered, for power delivered, we'll be now say it is just delta V squared over R. This gives us the power delivered, or the other one, delta VI. Okay, why do we say that? Because this one deals with the delta V, and we know that this delta V, from here, we also know that delta V is just IR. So delta V only works with outside the circuit. So this will be the power delivered outside the circuit. Outside in the circuit, but outside the source, okay? So that delta V is this one here, okay? Then if we then add the one from the inside, then we'll get the EMF. But this delta V is just the one outside, and it gives us the power delivered. It will give us the power delivered, okay? Not the power generated. Can you see that? Are you able to see it? Right, so this will be the first part. You just need to know EMF, you need to know maximum charge, power generated, and power delivered, okay, or power delivered. Now, in this power delivered, we usually will be using this one though, delta V times I. So put a star on it. This is usually going to be for our power delivered. Now, delta V times I, okay? So this is going to be the one most of the time for power delivered. Now, the thing of it is, once we know this, we are then supposed to talk a little bit. We are not yet done though. We're not yet done. We've talked about the power, the two formulas, power supplied, power delivered, maximum charge. Okay, this is going to be the maximum charge. You're going to see it, us using it just now. Okay, when we're talking about the equation of charging and discharging of a capacitor, this will be our EMF. Okay, now let's put the other things now that we were going to need to know again is going to be now, let's put it a little bit of theory, which is going to be, the first one is going to be KCL, which is Kirchhoff's, it's called Kirchhoff's junction rule again, or Kirchhoff's current law, okay? KCL is the current law, or Kirchhoff's junction rule, okay? What does this say? This one just says that if you look at a junction is going to be a place where you have more than two, okay? A place where you have like more than two wires coming together. So when you're talking about what happens at a junction, then you'll be saying that the sum of the currents, it's called Kirchhoff's current law because it talks about sum of currents. We'll be saying now the sum of the currents, entering a junction. I'll remind you this one when we do questions, but this is the sum of the currents that are entering a junction is equal to the sum of the currents, sorry for that, is equal to the sum of the currents directed out of the same junction, or leaving that same junction, okay? Directed out, or you can say leaving the same junction, okay? Leaving the same junction. So if we say the currents that are going into the junction, this should be equal to all the currents that are going out when you combine them together. This is going to be the junction rule. And if we have a junction, we say we'll be having, usually we put it like this, we'll be having more than two wires coming together like this. Here we have three. So we can have this current coming in, this one going out, and we can even have this one coming in or this one going out again. We call this I1, we call this I2, we call this I3. So we'll be saying I1 is the sum of the current going into, this should give us the sum of the currents coming out, I2 plus I3. This is going to be Kirchhoff's current law or Kirchhoff's junction rule. Now, once we know Kirchhoff's junction rule, we go to Kirchhoff's loop rule. And Kirchhoff's loop rule just now says that we say the sum, so Kirchhoff's loop rule, or it's also called Kirchhoff's voltage law, okay? This KVL or Kirchhoff's loop rule, let's put Kirchhoff's loop rule. This says now that, the sum of all the potential drops, so the sum of all the PDs, across all the devices or across all the elements in a closed loop, of all the elements in a closed loop, okay, must be zero, okay, or you can say is zero, or they must be zero. The sum of all PDs across all the devices in a closed loop is zero. So we are going to sum all the PDs and we are going to make them equal to zero. Now, what you must know is that when we apply, so for KVL, it's for PDs, which are delta Vs. It's going to be delta Vs. So we're going to say the sum of EMFs plus delta Vs, okay, plus the sum of these PDs. This should just give you zero. This is what the KVL says. All the potential drops across a circuit should give us zero when we add them, all the potential, all the PDs, okay? Now you must know that this is sum, this is delta, like this, okay? Then of course this is the EMFs, then these are the delta Vs. Now from here we are going to be meeting, this is a very important thing, let's just put it before you should know that when we meet a resistor, our delta V is going to change into an IR. We're going to change our delta V into an IR. And when we meet a source, our delta V will change into NE, okay? It will change into A. And then we will check the sign for us to know, is it going to be negative or is it going to be positive? We'll work on how to check. But first, just know from this video that we are going to look at the sign, at the things, if it's going to be, so delta V is going to become IR, delta V is going to become E. Looking at what you have, this is going to be when you have a resistor, okay, as your device. This is when you have a source as your device. This is then what just happens. Can you see that? Now, before we call this quiz, there are two more things that I want you to put. Here we were just introducing you to the ideas. We're going to talk about, when we do the KVO, we're going to talk about how you then know the signs. Is it always a positive IR or can it be negative? We're going to find the situations that make it negative. Now, the thing of it is, sometimes you see this KVL, usually you're going to apply it when you have two loops. Let's say one is a thingy like that, then another one is a thing. So you're going to have this one loop and this other loop, okay? Or you could have it like this. It comes like this. It goes like this. Then we have another one here, okay? Or even like this, we have a loop in here, we have another closed loop in here. So this is what we do. Now, when we are dealing with loops, sometimes you can get a circuit with only one loop. And when you get a circuit with only one loop, it will have here its source, here its resistor, here a capacitor, and it goes on. There is only one loop like this. When you get only one loop, then when you apply this KVL, you're just going to make sure that the source, if you have one loop, you don't even need to know the rules for how to make the signs be positive or negative. You don't even need to know that. You are just going to remember that it's going to be delta V of this battery. So we can write it as delta V battery, which is the E. Then we say plus delta V of the resistor plus delta V of the capacitor is equal to 0. This is an equation for you to already know. Please write this down for situations where you have only one loop, okay? So whoever you are looking for, you're just going to take these guys to the other side, this delta V and whatever, and there'll be negative on the other side, depending on who and whatever you are looking for, okay? This is going to be these delta Vs, right? Now you may be, for a circuit with one loop, so this is a single loop circuit. For this circuit with one loop, you may need to know this delta VR. Okay, one of them you may need to calculate them, or this one. So you should know that you'll be saying delta VR is going to be giving you negative IR all the time. Don't even try to make it positive. Why? Because these are the places. If it's only one loop, then obviously there's going to be a drop on the resistor and a drop on the capacitor. So when we do our capacitor, it's going to be delta VC is equal to negative of Q over C. Okay? Put it. This is another one to remember. These are the formulas to remember. Remember this formula which I've put here. Then remember delta V is negative IR. Delta V for capacitor is going to be negative Q over C. Why? Because there's always going to be a drop. That is for one loop. For the other things, we would have to look at the signs and whatever. But if we have only one loop, then this is where they will gain, because that's the only source. Then there's a drop here and there'll be a drop here. So that is why I treat them to be negative. So negative and negative. Can you see that? I hope you have seen it. Now the last thing which we are going to do is the last thing is just going to be charging and discharging of a capacitor. Okay, so when you are charging a capacitor, the equation for that is going to be, remember to charge is to add charge. You will now want to find how much charge is in the capacitor at any given moment. They can say after 6 seconds or whatever. To get that, you are going to multiply the maximum charge, which we saw that this Q is a CE. We saw it at the top there. Then you're going to multiply 1 minus, then e to the negative t over tau. Okay, this gives us the charge when we are charging the capacitor. When we are discharging a capacitor, then we'll be saying now this Q, the charge in the capacitor, is going to be just this big maximum charge. Then we multiply e to the negative t over tau. This gives us the charge on the capacitor when it's discharging. Then the last thing is, how do we then get this tau? This tau is going to be RC. Okay, it's going to be resistance times capacitance. Then we'll be having that tau. So this is it with the formulas. If you want to put the graphs for charging and for discharging, for charging, the graph is going to be like this. Then it becomes flat like that. Okay, here is going to be your maximum charge, which is QCE. Okay, then there's going to be one time here which is going to be special, and that time is going to be tau. So tau is going to be a special time which gives 63.2% of the maximum charge. This is going to be tau. It's time. Tau is time. So it gives you 63.2% of the maximum charge. Okay, then the maximum charge is this value which you'll be having up here. Now for discharging of a capacitor, it will be just like this. Here we have charge, here we have time, and the charge goes down as the time moves like this. This is for discharging. Okay, capacitor. Do you see that? And this is where we will again have our tau. Okay, tau, which is RC, of course, which is equal to 63.2% of the maximum charge. Either way, this is going to be our graph and we would be done. So this is now for discharging and then this one is for charging. Okay, do not forget. Now that is it. We continue in the next video where we now do questions and we are done here with everything. So goodbye.